our next step in looking at rotational motion is to look at rolling motion and what the moment of inertia is and what this all means. So this is going to be about rolling motion and the moment of inertia. So rolling motion is a combination of rotational motion and linear motion. So it's the motion of the wheel spinning and then the wheel and the object it's pulling going in the linear direction. So it's rolling and linear. And so we look at this wheel in this example. If we want to find the velocity here, it's 2 radius angular velocity. The velocity smack dab in the middle is going to be radius and angular velocity. And that's because that's the radius from the ground, and that's 2 here. All right, but we can find that velocity, but when we talk about rolling motion, that's what we're looking at. So an example would be a car whose tires have a radius of 32 centimeters, travels down the highway at 25 meters per second. What is the angular speed of the tires? So we look here. Our linear velocity is radius times angular speed. Our linear velocity is 25. The radius is 0.32 meters. We want to solve for angular velocity. So we do this math, and we get 78 radians per second. And that's the angular velocity. But that's how angular velocity and linear velocity then work together. So other terms, moment of inertia, how easy or difficult it is to change an object's motion. So the higher the moment of inertia, the harder it is to change its motion. So the larger the moment of inertia, the more difficult it is to start or stop it. The moment of inertia depends on the mass and the distance squared. And so we'll look at some examples of that. But it depends linearly on the mass and the distance squared. So moment of inertia of a single object. Mass times radius squared, units, kilograms, times meter squared. If we have multiple objects, we just add up the moments of inertia with the units being the same. And this is when we have things running into each other, or two different things, two different sized tires, and a car, or 2 wheels on a bike, or whatever. But the moment of inertia here, again, tells us how easy or difficult it is to move the object, or get the object to stop moving. So here are various shapes and sizes, with m being the total mass. So a hoop here, a disc which is filled in while the hoop is hollow, has 1/2 to it. If we got a disc or solid cylinder that rotates here at the rim, we have a different moment of inertia, and so it's based on location of rotation, which you can see here and here how it's different, and in the shape. You don't have to memorize these equations, just understand they do exist, and we're going to show you how to use this here with the next slide. So we have 2 objects. We have a disc and a hoop. Okay, so this is our hoop, and this is our disc at the top of an inclined plane, and we're releasing them both at the same time. Okay, which one reaches the bottom of the plane, or does the disc reach the bottom of the plane before or after at the same time as the hoop? So disc and hoop. Here's our hoop. Here's our disc. Okay, so we're looking at the moment of inertia, the I here. Okay, so the I for the hoop, when we look at the I for the hoop, okay, the hoop has I mr squared. And for the disc, the moment of inertia is going to be 1/2 mr squared. So which one has a higher moment of inertia? Well, if we consider mass and radius to be constant, obviously the hoop, all right, our hoop right here has the higher moment of inertia. So if the hoop has a higher moment of inertia, it's harder to get moving, which means the disc will get moved not only faster, but it will hit the ground first. So does the disc reach the bottom plane before or after? Obviously it reaches after, because, or the disc, I'm sorry, gets there first because the hoop has a larger moment of inertia. Okay, other equations that could come up, rotational kinetic energy, again, very similar to kinetic energy we saw when we talk about straight line objects. It is 1/2 moment of inertia times the angular speed squared, still joules as our units. Angular momentum, again, mass times speed. We got moment of inertia, I, times the angular speed, okay? Units, same as we saw with momentum before. So momentum and rotational kinetic energy, angular momentum, rotational kinetic energy, two of the same. This last table kind of shows connections between linear and angular quantities. Mass, moment of inertia. Velocity, angular velocity. Kinetic energy, rotational kinetic energy. Momentum, angular momentum. F equals ma, and we're going to get to this one next, is torque. Okay, so force and torque go together. Moment of inertia times its angular acceleration. But all of these work together. And on the next video, I'll give an example of a problem where you'll see this happening.